Good morning, everyone. Well, it's interesting. We're getting into some more rainy weather, but I'm okay with that. It's interesting with the congestion and all, and I think we all vary differently with that. But I hope everyone's doing well. I want to mention that we will have our final exam next week, and towards the end of the week, I will post an announcement about that. The uh, testing window will be similar to what we've been enjoying for all the tests we've had so far, so that will not change. And I will have that posted. I've already had some inquiries about when it will be, but it'll be around the same time. I have to do a great amount of planning when I look at my classes and decide how I want to configure the final exams so it provides flexibility for everyone. So I will have information up about that, but it will be very similar to what we've been doing with our previous tests. Um, Again, I want to say in general that the performance on the fourth test did show some improvement. Uh, I still see some work that doesn't seem to be exactly your work. I mean, I'll see answers to questions that tend to repeat from the homework sites, and usually they're incorrect or they're convoluted and they're not what I have taught you. But that's decreasing, so I'm glad for that. I am a nice person when it comes to being considerate of my students. I do expect you to do your work, and I expect you to maintain the schedule that I provide because it's very generous. But with the last test, again, I go through every problem. If your response on Blackboard is not supported by your work, I deduct points. You know that by now. And so please go to the solutions and look through those. These, of course, are solutions based on how I teach you. When I select problems for an exam, uh, I make up some problems. I select standard problems from the textbook. I select standard problems from a number of sources that tend to imitate the type of problems that I consider to be important. And they were all very fundamental. Some of the factoring questions some of you struggled with, and some of you struggled with some of the basic applications of the law of sines, which really was interesting. And again, with the equations and all, the techniques I taught you were the ones that I actually wanted you to use. Uh, Avoid squaring when you do trigonometric equations, ladies and gentlemen. That I did not teach you to do that, though most of you do it anyway. You did not use the lemma, which I taught over and over and over in the class. So just be aware of that. The techniques that I provide will actually help you. And if you have listened to anything I've said, by the time you get to Calculus 2, you will have hopefully enough memory of this material to be able to do well in the class. I know what I'm talking about, and I do know that some of you resist some of the techniques that I teach, and that's understandable because you're very young and you think that you know everything, and that's okay. I love confidence. Confidence is very important. Professor Ron was very confident when he was a kid, and I live for that. But just remember that I understand what you have to do in your following courses, and I know the types of difficulties that you will encounter. And so I salute all of you that are working hard. Again, remember the final exam will be 30% and it will be graded the same way. So again, stick to your own solutions, avoid solutions from homework sites. That will not help you out. And if it tends to increase at all, your grade will be converted to a 0. So I'm just letting you know that I appreciate the fact that you are trying to wean yourself from the homework sites. And then of course, some of you don't use them. I know this. This is not a blanket statement, but just remember that integrity is important, and your grade at San Jacinto College will carry weight because you have earned it. So do not put me in a situation where I have to uh, execute something that may not be to your liking. I'm very serious about my role at San Jacinto College. My respect as a math professor is very high. I do know that I get criticism for being difficult, but I'm difficult for a reason, because you are STEM majors, and STEM majors will change the world. So the next time, again, you want to complain about the difficulty of a STEM math class, don't. To be excellent in STEM requires paying your dues, requires reassessing how you actually do mathematics. And I do want to salute several of you. If I wrote on your uh, uh, test work comments, I said some good work, that is an excellent compliment. Jeremy, I just want to salute you for excellent work. Your improvement has been very good. I'm calling you out because your work was very good, and I think you can even bring it up for the final. All of you, I'm very pleased. And I want you to continue to work hard. So when you get to Calculus 1 and Calculus 2 and Calculus 3, you're just riding high. You're thinking, oh, thanks, Professor Ron. I know how to solve this trig equation. Or thanks, Professor Ron. You know, I'm glad you made me work because I can do the algebra. Trust me, ladies and gentlemen, this will pay off. And so keep working. Now, and also let me remind you, oh, and Simon, good job too. I want to salute you too. You're gonna make it. Just keep working. Your what is it? The signature assignment is due at the end of the week with the quiz and the homework. I tried to push everything to the end of the week to give you more time. Please get that done because it'll just be a standard quiz grade. Okay. And it's a simple problem on the law of cosines. A lot of you have said, well, it seems to be asking the question several times. Just focus on the very first question and work through the problem and answer the questions. You don't have to type it. You can write it out and you can scan it just like you're doing your test work. And that's fine with me. I'm more than happy to see that. So enjoy that problem. It's not difficult. You're thinking, why didn't you put a simple problem like that on the test? So enjoy that. Now, today, what I want to do is to discuss mathematical induction. Now, what's interesting about this is that you already know induction. I know I say this all the time, but you already understand the natural numbers. And what we want to do is take advantage of that so that we can prove logical statements about natural numbers. They actually abound in calculus, even though you're thinking, well, calculus is not really discrete, Professor Ron, it's more the continuum. But we have sequences, we have discrete topics that find their way into calculus, just like taking derivatives of power functions. We can't get away from it. So let me go ahead and share my screen. Now, one thing that I want to do to get the ball rolling, and I thought, well, I'll just do an example. And then I thought if I do that, then everybody would be like, well, what is he doing? It seems like he's just making this up. So let me go ahead and give you the principle of mathematical induction. So we're going to say mathematical, very long words, mathematical induction. Mathematical induction principle, or the principle of mathematical induction if you're from Great Britain. I don't really care how you say it. The idea is that it is based on a property of the natural numbers, that every subset of the natural numbers has a least element. Okay, that is an axiom. If you take a subset of the natural numbers, 1, 2, 3, 4, 5, etc., if you take a subset, there will always be a least element. That is an axiom. Just like commutativity of addition of real numbers is an axiom. If you say 2 plus 3, that equals 3 plus 2. There is no question about that. That is an understood statement. So what we want to do is let P of n be a logical statement about natural numbers. So when I say P of n, it could be one of the famous formulas. Let me give you an example of P of n. We've already done the famous formulas. We could say the sum, I'll just use an I, equal 1 to n of the first n natural numbers. This is 1 plus 2 plus 3 up to n equals n times n plus 1 over 2. Now, we could prove that many ways. One way is through induction. So this is a statement about natural numbers as a formula. Sometimes the statement might be as an inequality. Who knows? It might be about a certain sequence of numbers that has a particular formula. It just has to be a logical statement about natural numbers. And you think that it has to be kind of like a domino effect, because we can test it for one natural number, test it for another, test it for another, and then we say, when do we stop? So that's the idea, to minimize the amount of work. So here's an example of a logical statement. Another one, here, I'll give you an example of some that we're going to do in lecture. Let me give you another one, P of n. We can say, and I'm going to give you some notation so it's actually good for you. We can say 5 divides. Now divide, this vertical line is going to means division, divides. That means that 5 divides evenly, no remainder. Divides 8 to the n minus 3 to the n for n greater than or equal to 1. And again, in all these cases, n is a natural number, ladies and gentlemen. So in this particular logical statement, I'll say that the expression 8 to the n minus 3 to the n, where n is a natural number, is always a multiple of 5. 5 divides it. That's another logical statement about natural numbers. Okay, so when like I say, we can start substituting numbers, and we can say, well, let's just add the first 3 natural numbers and check the formula. Let's replace n with 2 and see if we actually get a multiple of 5. And we say, oh, it does work. Okay, so is that enough? Well, then you're thinking, how many natural numbers are there? There are infinitely many. So, okay, so do we check 100? Do we check 1,000,000? Do we use a computer? The thing is that when it comes to infinite sets, and we're thinking, when we do trigonometry, we're talking about the infinity of the real line. But when we do a proof, we do it in the abstract, so we don't have to check every possible real number. Okay, we always look to the reference triangle or the first quadrant to get the reference number. So that was our way to avoid having to do an uncountable infinite number of proofs. So when it comes to natural numbers, we look for the same type of execution. That is, we look to the mathematical induction principle. And how does it go? Well, to make life simple, and this notation Dr. Stewart uses, but I'm going to add an extra piece of notation. I'm going to say, let S be a subset of the natural numbers. Okay, that means containment, contained in. S is a subset of the natural numbers. And we're going to define the following. That is, S will be all elements of the natural numbers. I'm kind of overdoing it here, such that P of n is true. So if we look at this and we say, okay, maybe we should just do 3 or 4, and we see it works for 1, 2, 3, 4, and maybe we tried 10, it works for 10. Okay, so this is just going to be a set that keeps track of all the natural numbers for which P of n is true. Now, if we were doing that for this one and this one, is there a way that we could show that S is equal to n? That is, when we write these down here, we're not restricting the value of n. We're saying this works for any n. Okay, so our proof would have to allow us to make that leap. So here's how we can make the leap. So number one, so we're going to say if the following. If number one, that is one is in S, one is in S, that P of one is true, okay? And two, for now, some mathematicians use a different letter. The author of the book likes to use a K. It doesn't matter. You can use the same N. If you use K, it's fine. They're trying to make it look special, but you don't have to. If you want to use K and your homework uses a K, that's fine. You'll need to use the same letter. But the letter you use in this second part is immaterial. It doesn't matter. It doesn't make it right or wrong. So for some N in the natural numbers, for some N, so we're picking, there's an N, there's one specific one, some N, say 500. For some N, we have the following. If N is in S, this implies that the successor of N is in S, which is N plus 1. So 2 basically says for some natural number, we call it N, you know, sometimes it's called K, sometimes it's called J or whatever, it doesn't matter. The fact that N is in S implies that N plus 1 is in S needs to be true. So if this is true and this is true, then S is all of N. That's the key step. Now, what students say is, what is this? So basically, for some natural number N, I assume this. This is the hypothesis. And it has to show, that it has to be true that this implies that the next element after N is also in S. So students say, what is this, Professor Ron? This is called the induction hypothesis. Induction hypothesis. So first of all, when you apply induction, you test for the initial value. Maybe the formula doesn't work for 1. Maybe it starts at 2 or 3. There's an initial value, okay? And it probably doesn't really matter if you don't use 1, but 1 is the customary one. And in the proof, it actually does make sense to use 1, but maybe it starts at 2, but there's an initial value that you need to check. And the idea with that is it's basically saying there's a reason to move forward. If you can't get the formula to work for 1 or an initial value, then the formula is probably incorrect. Or maybe it's only true for certain values and it's not a true statement about natural numbers. So we check this first. This is easy. This part is never usually difficult. You don't need me for that, okay? Now for part 2, you basically assume this formula here for a specific N. Okay, you're assuming this is true. Usually they'll use another letter like K to make it look special, but you don't have to do that. But if you see that, it doesn't change the argument. I just think fewer letters, the better. So what you have to show is that if you assume that the statement is true for this particular N, that it will force the statement to be true for the next value of N, that is the successor. And that is called the induction step. Now, when you think about this again is what you suppose. We assume this and we show that by knowing this, we get this result. So if you prove a statement about natural numbers by induction, you must use this. Students will get happy and say, oh, I proved it by induction. I said, well, you've given me a proof, but it's not induction, okay? You can't you can't do induction unless you use the induction hypothesis. So basically, it's like taking the result and saying, okay, now for some n, I'm assuming it's true. Let me use that to show that it's actually true for the next natural number, which is n plus 1. Now, the key here is that this is like the domino effect. This is for some n, and it basically turns out to be, okay, well, if it worked for this n, it could have been for an n you chose over here or an n you chose way over here. And the arbitrariness of this is what allows you to get the domino effect. The idea is that if you assume that the negation of this result, you get a contradiction. So this is actually a number theoretic construct that's very important because, like I said before, you actually end up needing inductive type arguments in calculus. We've already seen that doing trigonometry requires us to talk about natural numbers. I mean, we can't get away from it. So let's look at some examples of this. So when we do induction, I'll always showcase it this way, and this will be what S will be defined. I may not write down what S is, but it will be the subset that keeps track of all the natural numbers for which the given logical statement is true. Okay, so you could say, you know, we could define it even more explicitly with this, but this is going to help us to keep things very, very organized. Okay, so let's apply this to an example. Now, at first, this will seem a little bit awkward. I know this, but adhere to the recipe. The recipe will not fail you. What will fail you is that you just have issues with this, and this will be the part of the mastery that'll be the most difficult. So let's look at an example. Now, since I've gone ahead and I've given you some examples, I'll pick one of them that's easy. I'll do the one that we just, the last one that we gave. So here's our P of n. We say that 5 divides 8 to the n. This is the one that I wrote here. 8 to the n minus 3 to the n. For n greater than or equal to 1. So regardless of the natural number, and you're thinking, boy, that, you know, when you're working with number theory, you computer science geeks, computer engineers, number theory is why we can encrypt all of the software for major institutions in our government and our banking system. The number theoretic results in mathematics allow us to create software that keep everything safe. There was a time when number theory is considered irrelevant, and now it's the only thing that keeps us keeps our software safe, and it is a plus. So the idea here is that say you're trying to use some number theoretic ideas to construct a nice algorithm for a firm where you happen to be working as a STEM professional, and maybe you've got to work with some formulas like this. And of course, you'll have Fermat's theorem, Euler's theorem, all of these nice theorems about prime numbers that will allow you to do your craft very well. Those of you that go into computer science will take more number theory because it will be required when you do cryptography. So the idea here is, again, remember, we will define S to be the set of all natural numbers such that P of n is true. So our proof, this is where every time we do a math problem, we're doing a proof. So we'll just mark it as 1. We'll say n equals 1. That's what we have to test. So we need to show that 1 is in S. So we just look at it. So we say, in this case, 8 to the 1 minus 3 to the 1 equals 5. But 5 is just a multiple of 5, right? It's 1 times 5. So clearly 5 divides 5. So this implies that, now, if you like, you can say P of 1 is true, or I can just say 1 is in S. So usually this is very simple. I mean, 8 minus 3 is 5. 5's a multiple of 5, so 5 certainly divides it. 5 is 5 times 1, so boom, we've got that. That, again, the easy part. So you're thinking, all right, well, seems reasonable. So part 2, for some natural number n, again, you can use whatever letter you want, it doesn't matter. We're going to say n is an element of S. And let's just write out what that means. We're just going to basically say, when we look at this, that 5 divides 8 to the n minus 3 to the n. And in my notation here, this is where you can get creative. This will just say that 8 to the n minus 3 to the n is some multiple of 5. And so we'll just say 5. I just use the letter alpha. You can use any one you want for alpha, a natural number. So if 8 to the n minus 3 to the n is divisible by 5, which we're assuming this is the induction hypothesis, then it must be that this expression is a multiple of 5. So 5 times some natural number. Okay, this is where the abstraction takes this argument up a level and allows us to use the abstraction to prove this result. So now we're thinking, okay, what's the next expression? We have 8 to the n plus 1 minus 3 to the n plus 1. So this, what is this? This is the induction hypothesis. Induction hypothesis. Hypothesis. Then this is where you have to say, okay, well, what do we need to show? We need to show that 8 to the n plus 1 minus 3 to the n plus 1 is actually a multiple of 5 using this fact. So this is where we're going to have to get creative with the algebra, where we add and subtract a term that will allow us to reform this expression in a way that will show that it is actually a multiple of 5. So first, we'll use some laws of exponents. This is just 8 times 8 to the n minus 3 times 3 to the n. Now, we're thinking in this particular case, and what's interesting about a situation where you try to make something morph into something that's going to be helpful is the following. So notice here, this is going to be an important part. So we're thinking, if we want to be able to use this, we need to be able to factor this in a way so that we've got at least a factor of this, and then maybe a multiple of 5 that just is 5, okay? So here's something we're going to try. So in this particular case, I'm going to try 8 times 3 to the n plus 8 times 3 to the n, and then tack on the very last term here. Now, this isn't necessarily unique, but look here what we're thinking about. Notice this is an add and subtract. Add / subtract, not necessarily in that order. So when we do this part here, this is basically adding a 0. But it's allowing us to use this, because when we look at this, we think, okay, if we factor here, we expose the 8 to the n minus 3 to the n, which is a factor of 5 by the induction hypothesis. And when we factor here, we're left with 8 minus 3, which is 5. That's clearly a multiple of 5, which is 5, Okay, so the key here is that we want to add and subtract a term that will allow us to use this. And this is by no means unique. It's simply one that works. And you might try something and say, that's not quite what I need. Let me adjust this a little bit. So the induction step, which is using two, is the most challenging. In some cases, it can be very straightforward. In this case, you really do have to think about it. But once you adopt this technique, you can reuse it. So now we're going to factor by grouping. So factor the 8 in the first two terms. 8 to the n minus 3 to the n, right here. And here we're going to factor the 3 to the n. Now, what's nice about this is that this is where we get to use the induction hypothesis. So the reason for adding and subtracting this term was basically so that we can actually use this hypothesis. So now this is what 8 times 5 alpha. That's a multiple of 5 because it has a 5 in it. And 8 and alpha are just natural numbers. Then plus 3 to the n times 5. Okay, so we have basically two expressions that have 5s in them. So we can factor the 5. Eight alpha plus 3 to the n. And this is a multiple of 5. A multiple of 5. Now, of course, this is just a natural number, 3 to the n, where n is a natural number, and 8 alpha, they're all natural numbers, a natural number plus a natural number. So this is indeed a multiple of 5. So if we run all the way back right to here, we see that 8 to the n minus 1 minus 3 to the n minus 1 is also a multiple of 5 if we assume it's true for the previous natural number n, which we assumed was true. The induction hypothesis allows us to force the validity for the next natural number, n plus 1. So this is a multiple of 5. So this implies n plus 1 is in S. See, my notation does actually work. We get that n element of S gives us n plus 1 is in S. So this is where you have complete flexibility. There is no required technique for the induction step. The thing is that you can utilize any algebraic manipulation that encompasses the induction hypothesis legitimately to go from here to here. And once we have that, here we have 1 is in S. N in S implies n plus 1 is in S. Then we're done. Then S is all of n. So now this is how we finish it so we don't have to write forever. By induction, S equals n. Now, I used to write, well, by induction, P of n is true for all natural numbers n. Well, you know, ladies and gentlemen, after a certain amount of time, it's like, why do we keep writing the same thing over and over? Let's just go ahead and write this and phrase our induction hypothesis in terms of S. And then if S equals n, then we know that P of n is true for all natural numbers. So we're not like, you know, we're not getting tired just by writing down the obvious over and over. If we systematize this efficiently, then our result is elegant, just like we solve trigonometric equations, just like we solve anything. The key is that we always want our work to be valid, okay? But we do want to make sure that, you know, as we learn, you know, the first time you work through it, it's all here and there and you're trying to hone your expertise. But then you want to say, okay, let me stick to this notation so that I'm actually doing something that's efficient. So now we're done with that. So you can go back, you don't have to believe induction. You can go back and check any power of 8 and n, take 8 and 3, take the difference. You know, you can use your fancy calculators. You can use your Google calculator. The thing is that the theoretical power transcends the computer. You have to have a really, really nice computing system to be able to generate natural numbers that will be this large. And that's where the power of the mathematics transcends the calculator. We love our Google calculator to get a nice calculus approximation, but it's the calculus that makes the calculator work. Okay, it's not the reverse. And that's the big problem with math these days. No one wants to do the hard work. You know, I'm a big, like I say, I'm a big fan of the technology. We love it. We love our cell phones. We love our computers. You know, we love Zoom so that we can have class. But the key is that the mathematics we do here enables us to use our technology with some degree of confidence. Okay. So now you see this, you could sit with your fancy calculator all day long and check values of n and get absolutely nowhere. You might think, oh, I think this is true. I think this is true. How do I prove it? Induction. Okay. So there's a big argument. You know, I did an algebraic proof. Do I need to verify it by induction? There are purists that say you always need to verify, but we have actually gotten some proofs about natural numbers that have been valid. It just really depends on how you want to characterize it. So I would tend to say that if you get a nice legitimate algebraic proof, then that's sufficient. However, if you kind of work to a formula that you think is true and you want to verify by induction because it's about natural numbers, that would also be a valid path. Again, there are very many discussions on how to be completely mathematical with things, and I don't believe that you should get stymied by arguments just because you're thinking, you know, we're now splitting hairs because it's all about semantics. Let's just say that if we have a valid proof, then we'll stick with it. But if we're not sure about our proof and induction will help us to finish off the problem, then we'll do it. And let me move Professor Ron over a little bit. Okay, let's try another one. Now, I've got several examples here. The famous formula is really easy, so I wanted to do one that was maybe a little bit more challenging than that. Let's see, here's a good one. This is going to use some college algebra. So here we have P of n will be the following, and let me not say equals here. This is going to represent the actual statement. I'll write it in two ways. I've written this up in the Smart Pen videos. We just basically sum the cubes of the odd natural numbers. So this is different. So basically what we're doing here, we're taking the odd natural numbers and we're cubing them and taking the sum. So the first n cubes of the odd natural numbers. So we're leaving out the evens. So 1 cubed plus 3 cubed. Remember, we had 1 cubed plus 2 cubed plus 3 cubed. That was the famous formula. This is not that. This is different. So we're leaving out the even cubes, and we end with the nth cube here, odd number. This has a formula, and it looks like this: n squared times 2n squared minus 1. Now, of course, you're thinking, if you come about this formula through an algorithmic process, that's fine. That's fine. Here's what's interesting. Lots of formulas are deduced by experience. And so you're thinking, I've worked with this some. Every time I work with it, I'm finding that these numbers are rising. is this valid for all natural numbers? And we're saying that it is. So induction is kind of like a procedure to say you've been working with a set of numbers in a certain construct, and every time you work with it, you're getting this pattern that starts falling out, and you're wondering, is this actually true, or did I just get lucky 5 or 6 times? So the key here is that this is actually valid, that this is true for all natural numbers. So this is a statement about natural numbers. So if you wanted to, you could write it with the sum. I think I used an I here, or you can use whatever letter you want. Let's see here. We have I equals 1 to n. And we could write this way. We could say 2I minus 1 to the nth. Write it that way. And so basically here, when I is equal to 1, we get 2 minus 1, which is 1. When I is equal to 2, we get 4 minus 1, which is 3, and we're cubing it. Now, of course, I don't need an n here. I just need a cube. And so now when I look at this, this is a compact way of writing this sum. And of course, when n, we get to the largest index here, 2i becomes 2n minus 1, which is that argument cubed. So this is the shorthand for this finite sum. So that's just good practice writing sums. And this equals n squared times 2n squared minus 1. Now here's something that I'm going to show you. It's not going to be hard to check that 1 is in S. And then we can assume basically this formula right here. We can assume this formula for our computations. And then we're thinking, what are we going to do? We're going to add the next term, because now we have to add up n plus 1 terms and see if we assume this formula, we get the basic formula here where n has been replaced with n plus 1, basically. And so we're thinking, okay, so can I just replace n with n plus 1 and be done? Well, no, that's the key. That's the linchpin of the problem, so to speak. We have to assume the induction hypothesis and then show that that formula comes out of that construction. So that's where the difficulty arises. But what we can think of, little to the side, here's a little sidebar. And this is how I want you to approach these problems. You can write your sidebar and say, well, the goal would be, if this would work to add the first n plus 1 cubes of the odd natural numbers, the result should really be n plus 1 squared times 2 times n plus 1 squared minus 1. That would be what would have to fall out of our computations if this were actually true. We can't just go in and replace, because we have to prove that this is the result, okay? So this is really what our goal is when we've got a formula like this. Unlike the last problem, which just basically was forcing us to show that 8 to the n plus 1 minus 3 to the n plus 1 was a multiple of 5, if we assumed it true for 8 to the n minus 3 to the n. And that we could do by adding and subtracting a convenient term. So now let's go ahead and do our proof. So now that we kind of see the difference between these two methods, let's go ahead and effect the proof. For number 1, we'll just let n equal 1. Okay, so here, that just means we have one term. So we have what? 1 cubed. If n equals 1, then there's only one term, and that's just this. Does this equal the formula? Well, let's just substitute 1 squared, 2 times 1 squared minus 1. Well, that's just a 1. And of course, that's a 2 minus a 1, which is clearly 1. 1 times 1. So, you know, that didn't take much work. So this implies that 1 is in S. Again, remember, S keeps track of all the natural numbers for which this logical statement is true. All right. So now for 2, for some n element of the natural numbers, n is an element of S. What does that mean? It just means this. We'll just write it down. That for this particular n, if we add up to n these cubes of the odd natural numbers, we get that formula. So we're just basically restating the theorem. Now, of course, if you want to use k's instead of n's, you can. It makes absolutely no difference. I don't believe in new letters. The thing is that here, the n is for any natural number. Here we're picking a specific n. For some n, we're saying this is true. So your choice. So this is our induction hypothesis. So write induction hypothesis. You can just shorthand it in end hip. Induction hypothesis, but not hypotenuse, hypothesis. So maybe that's not the best abbreviation. So now when we look at this, we're thinking, okay, so if I add the next term, which will be 2i plus 1 cubed, and I assume this, is that going to be the result? Well, with some work, it will be. So now, then, if we look at it, I equal 1 to n. Oh, and now we're going to go up 1, n plus 1, 2i minus 1 cubed. So now we're going to add the first n plus 1 cubes of the odd natural numbers. Now, of course, we'll break it up. This will be I equals 1 to n of 2i minus 1 cubed. And then, of course, when we have the n plus 1, that's going to give us a 2n plus 2 minus 1. So that's, and of course, subtracting the 1 gives us a 2n plus 1 cubed. Okay, so basically, we're just adding the next cube of the next successive odd natural number. That's it. What does this equal? It equals that. So now and here's what I usually do. It's like doing calculus. We do L'Hopital's rule. We'll do induction hypothesis right there. Induction hypothesis. So for this, we can replace it with this. So this is n squared times 2n squared minus 1 plus 2n plus 1 cubed. So now we get to use our formula from the first week of class. This is really the binomial theorem, which we're going to talk about next class, but we get to use it. I wanted to do this because this problem allows us to use all kinds of algebra that we've already worked with. So it's something you can understand very readily. So now when you look at this, you're like, woe is me, Professor Ron, I don't see that equals that. Well, I'm going to show you how we can do it. We're going to treat this like a polynomial in n. Otherwise, you can't really look at this and get that quickly. So what I want us to do is collect all the terms, multiply it out, collect the terms, and then use rational zeros. So let's do it. So we're going to get an n squared, so we get 2n to the 4th minus n squared. Now, that was the easy part. Now here we're going to cube. So we've got, this is a 1, so hallelujah, that's easy. So we cube it, then we square it, then the first degree, and then a 1. So remember, I'll just write this up here. Since that's a 1, let's just do a special formula. This will be a cubed plus, and this is where we have to remember when we actually expand things, we have the binomial coefficients. So this is going to be 3a squared plus 3a plus 1. That's the special formula when the b is equal to 1. Or you can just multiply it out. So now let's write it. So we're going to cube, so we get plus 8n cubed plus 3 times 4n squared plus 3 times 2n plus a 1. Okay? That's using our special binomial formula. So we get 2n to the fourth minus n squared plus 8n cubed plus 12n squared plus 6n plus a 1. Now we're almost done. We'll just write it in descending order. Notice here, and you all are getting better about not using slash lines. If you use them this time, I just ignored it, but don't use them. It just doesn't make your work look smart. If anything, it looks ridiculous. So just quit using them. Do the connection and do the work in a way that is easily read. So now we've got 2n to the fourth. And now we see we've got what 11n squared, but this term precedes it. And then we have a 6n and we have a 1. Now, you're thinking, how did this improve anything? Well, the thing is, and what I thought about this particular example was that sometimes when you're doing these types of problems, the algebra is simple because you just factor, maybe an AC method, AC lemma, and you're done. Here you've got to be a little bit more refined in your reasoning, because when you look at this, you're thinking, okay, there's my sidebar. So by knowing where you need to go, lots of times in mathematics, that helps us to construct an argument. Because, for instance, maybe you've checked this for lots of powers of n, and you're like, oh man, I need to really use this for, I need to assume this is always true for the natural numbers. How am I going to get there? How am I going to convince my colleagues when I present this that this is actually valid? Well, so here we go up to the sidebar and see that in this particular case, -1 is a double root, okay? -1 is a double root. And so that will allow us to reduce this twice and we'll get the result we need. So here's what we do. You just do your little synthetic right here. So again, -1 is a double root. That's the old terminology. A zero of multiplicity 2. That's what you all say, but Professor Ron grew up with the old, is a double root. -1 is a double root. So we'll just say 0 of multiplicity 2. So we can break this down using synthetic twice and we're done. So do your little sidebar here. Do your -1. So we have your 2, 8, 11, 6, and 1. So bring the 2 down. So we have a -2 plus 8 is 6. -6 plus 11 is 5. -5 plus 6 is 1. And -1 plus 1 is 0. So there's our reduced right there. So this gives us n plus 1. We have 2n cubed plus 6n squared plus 5n plus 1. Again, the power of the mathematics is understanding how to use it, okay? And that's how I teach. I don't do anything unless I talk about it for 20 minutes, unfortunately, but that's how you learn it. Now, of course, we go back up here, we've got a double root, so we can do this again. Let's do our other division here. So we have 2, 6, 5, 1, do another -1. So we get 2, -2 plus 6 is 4, -4 plus 5 is 1, -1, 0, reduced right there. So now we have n plus 1 squared, and we have 2n squared plus 4n plus 1. And now this is exactly that. And we're done. So let's rewrite it. So this is n plus 1 squared. And this is, if you like, 2n squared plus, now what we can, here, let me write it this way so it'll be a little bit more believable. This will be, in this case, n plus 1 quantity squared times a 2. Now, when we do this, notice here, if we write to the side, 2n squared plus 4n plus 2 equals 2 times n squared plus 2n plus 1 equals 2 times n plus 1 squared. I didn't want to write all of that there, so it's better to do the little sidebar. But of course, this is 1 too many, so we subtract the 1 here. So from here, you can just kind of run over here and do this little sidebar. And so now we see that this is exactly this. So this implies n plus 1 is ns. Now, of course, the key here, and again, when you look at this, you've got this as the goal, and then you see that 2n squared plus 4n plus 1 is what? For instance, if you bump this up 1, this gives you this, and so you've got this term. This is 1 too many, so this basically implies that 2n squared plus 4n plus 1 equals 2 times n plus 1 quantity squared minus 1, which is what we needed. So you could put all this in the proper, but I like maybe just to do a little sidebar here so you can see that. It's your choice. It just really depends on how you look at it. So this particular type of argument is a little bit longer because the algebra is less straightforward. But when you look at it, this is a really, really good problem because the induction step is the most difficult. You're thinking, how am I ever going to make this look like that? Well, write down what it would look like if you replace n with n plus 1, and then say, okay, let me treat this as a polynomial in n. This tells me that I've got a double root of -1, apply synthetic division twice to reduce, and then recast this in terms of that just by making this comment here. And then, of course, if we have n element of S implies n plus 1 in element is an element of S, this says by induction, S is all of n. So again, the beauty of induction is that you could not check this for every natural number. And you're thinking, well, it seems right, but that's not a proof. And unfortunately, when you're dealing with numerical constructs, you can often think, oh, well, that would be true. I mean, back in the days, many people thought they understood prime numbers, and they'd say, oh, here's a formula that generates prime numbers, but they never worked because they didn't pass the induction test. The thing is that certain formulas would produce prime numbers up to a point, and then they fall apart. So the key here is that number theory is not something that you can just kind of pass off as common sense. It often takes a little bit more work to verify. And so induction is a very powerful means of illustrating the validity of a particular logical statement about natural numbers. Some take more work than others. This is not an overly large amount of work. It just really depends on what you remember from the previous exercises that we've done, and then recalling again the rational zeros theorem because you looked into the future, you look beyond. Again, if you get here and you don't really look beyond, you're not really noting where it is you need to go. So when you've got a formula that looks like this and you're basically having to replace n with n plus 1 in an algebraic sense, then it's important to go to this point and say, oh, this is what I need to do. So let me make sure that my calculations lead exactly to that expression where I have what? Used the induction hypothesis. Okay, so let's try another one. Again, I wanted to do this one because it has a lot of algebra in it and it keeps you fine-tuned. Now, one that I thought was interesting was a simple inequality, which is actually something that's useful in calculus. Here's another example. It's called P of n. It's actually called Bernoulli's inequality, but it's not. Bernoulli is one of the Bernoulli brothers. They were all famous mathematicians, and I rarely keep their first names straight in my mind. So here is what we have. So we start out with a real variable, x must be greater than -1. So this is binomial in nature. That's why I'm doing it, because we're going to do the binomial theorem for positive integers at the next lecture. So I thought this would be a nice result to share with you that mimics the binomial theorem that we're going to talk about. If x is greater than -1, now this is important, greater than -1. So you got the number line -1, anything greater like -1/2, 0, 1, 2, 3, etc. -2, -3, things like that don't work. Then if we actually look at the following expression, power expression, this is binomial. 1 plus x raised to the nth power, n's going to be a natural number, will always be an upper bound for 1 plus n times x for n element of the natural numbers. Now, of course, there are times when you're thinking, well, we got an inequality, and that last thing we did, when am I ever going to use that? Well, you may not use it right away, but there'll come a time when induction, you're going to need to do induction, so you're glad you did the problem. There's going to come a time when you need to do rational zeros theorem. There's going to come a time when you need to actually use the binomial theorem, and then that formula may actually creep into your calculations if you're in a computer science class. So don't ever discount doing a problem that's difficult, because that knowledge will actually serve you later. So you're thinking here, we've got an expression about natural numbers. As long as x is greater than -1, this works. And so we're thinking in this case, all right, okay, so we've got this restriction on x, and we're saying that for all natural numbers n, 1 plus x raised to the nth power will be greater than 1 plus nx. So we have a lower bound, which is really simple. And that looks like just the first two expressions of the binomial expansion, just like we did before with the a plus 1. We just flipped it around and called it, now instead of 1 plus a, we call it 1 plus x. And then that case was a 3, and now we're generalizing. So we're thinking, all right, okay, so S will house all the natural numbers for which this is true. So we're going to proceed by induction. So number 1, let n equal 1. Okay, let's check it out. So here we have 1 plus x to the 1. We'll just raise it to the first power. So this is equal to 1 plus x. Okay, now we're thinking, all right, well, we can also say that, I don't know, 1 plus x is certainly greater than or equal to 1 plus x, it's equal to. So we can say greater than or equal to 1 plus 1 times x. Now that's kind of, it's not very earth-shattering, but it is true. 2 is greater than or equal to 2. I mean, that's true. So we're thinking, all right, well, it wasn't really difficult for 1. So yeah, 1 plus x raised to the first power is actually greater than or equal to 1 plus 1 times x. So good. So this implies that 1 is in S. That is, this statement's true when x when n equals 1. Now again, what's important here, and this is very important, at this point here, it doesn't look like so much we're so much bothered about x greater than -1. But what's important here when we start looking at this, this is going to take in a much bigger argument as we move to higher powers. So right now, it doesn't look like it's a huge deal. We're not thinking that we had to focus so much on what Professor Ron wrote there, but don't discount it. So this will actually become more important as we look at the induction step. So number 2, for some n element of the natural numbers, n is element of S. What does that mean? Well, it just means the statement here. 1 plus x to the n is greater than or equal to 1 plus n times x. And again, just as a little sidebar, remember x is greater than -1. So now we're thinking, okay, well, we assumed this, and this seems so much easier than the last one. We don't have all this algebra that's going to take up a lot of our time. So now we look at the next power. So the little sidebar here would say, what's our sidebar? What do we need? Well, the goal is that if we replace here n with n plus 1, we replace it there. So the goal would be 1 plus x to the n plus 1 should be greater than or equal to 1 plus n plus 1 times x. That would be the goal. That is, if we just simply replaced n with n plus 1, just like the last problem, that's what we're going to need to show is true. So that gives us a goal. So don't, when you've got all of these formulas in front of you, and you know that you have to show n element of S implies n plus 1 is an element of S, then write down what that goal is. It will help your reasoning, and it will help you to see, well, you know, if I really want to get to this point, my reasoning needs to go in this direction. So that's really just smart planning. It's like being an accountant. You know, you've got to have all your devices ready. You've got to have all of your accounts, and you've got to have all of the information from your client all available so you can make the best plan for doing their taxes. Okay, bring this in, use this rule, so you're lowering the tax rate. So the idea or the amount of tax, the rate is dependent on the income clearly. But the thing is, we want to have all of our ducks in a row before we start trying to make deductive steps. So now what do we have? 1 plus x to the n plus 1. Well, first, we're thinking, okay, well, we have an induction hypothesis. So this is going to be 1 plus x using the laws of exponents, right? So 1 plus x to the n plus 1 is equal to 1 plus x to the n times 1 plus x to the 1, okay? So just laws of exponents. And now, of course, we can replace. That is, we have a lower bound for this using the induction hypothesis. So we say greater than or equal to, in this case, 1 plus nx times 1 plus x. So this is induction hypothesis right there. So again, we assume that 1 plus x to the n is greater than or equal to 1 plus nx, so we can replace this with this and have the inequality. Okay, now let's just see what this is. Let's multiply this out because this is not, doesn't look like that. So let's just see if we can actually get that. So now we have 1 times 1, and then we have 1 times x, and here we have n times x, and here we have n times nx times x, so plus nx squared. Okay, now we look at this and say, okay, well, let's just see what this gives us. We've got a 1 and we have a x times an n and an x times a 1. That's starting to look a lot like that. So let's go ahead and factor. So we have 1 plus, let's factor the x. So we have x n plus 1. So that looks exactly like that. And then we have plus nx squared. Now, when we look at this and we think, okay, well, here's where this is going to come into detail. notice when we look at this, this is always going to be bigger. This is a positive construct here. That is, this is a positive regardless here. I mean, we've got this as being positive. And so now we can say, we can omit. So omit this. Make this actually smaller. So now this is actually bigger than what I'm going to write here. And I'll flip this around. 1 plus n plus 1 times x. Because this term here, by hypothesis, is non-negative. Again, if we square this, if x is greater than -1, then this is a non-negative term. So we can just omit it to get this. And then this is exactly what we need here. So if we cycle back, 1 plus x to the n plus 1 is indeed greater than or equal to 1 plus n plus 1 times x. So when you look at an example like this and you think, well, that wasn't so bad. The idea is maybe the estimation turns out to be very simple. Again, this is a non-negative quantity right here. This quantity is always greater than or equal to 0. And only being 0 when x is 0. This is a non-negative quantity. So if we omit it, then this will be less than or equal to this. And this is exactly what we need here. So indeed, it is true that 1 plus x to the n plus 1 is greater than or equal to 1 plus n plus 1 times x. So this implies that n plus 1 is in S. So by induction, S equals all of n. So again, you might look at some of these results and say, when am I going to use this? Trust me, this is a useful inequality. It will come back up and it will be something that you'll be able to utilize. I utilize this in analysis all the time. Right now, it's not going to be something that's going to be beckoning at your door, but it makes a great example for induction. Again, the x is fixed. The x is fixed. So for any x that you fix greater than -1, this will be true. And so n is allowed to vary. So this is indeed a logical statement about natural numbers. So what's interesting here is that we can bring in the real analysis with the number theoretic construct, the natural numbers. Now, the next example I thought was really interesting because we've been focused on trigonometry. So just look at this as a nice example. Put this on a note card. You will find uses of this. And if you want to check it out, Bernoulli's inequality. This is sometimes written Bernoulli's inequality. A very standard result. And a whole lot easier than using the binomial theorem. Trust me. So when it's applicable, it's a good one. Now, I wanted to throw in some trig. You know, Professor Ron likes the trigonometry. So here is an actual special case of Euler's theorem. So what we're going to do is fix, like we had the x before, fix the last problem we fixed x greater than -1, fix theta as a real number. Then, and this is a special case of Euler's theorem, this actually is called de Moivre. De Moivre, the theorem of de Moivre. And de Moivre, I believe, was French. So then we'll have cosine, we're going to get to use the imaginary unit, cosine theta plus imaginary unit times sine theta. This is a major result, which again is a special case of Euler's theorem. And I'm doing this because it's the binomial theorem, which is what we're coming up with tomorrow. But this is called the simplified binomial theorem. You don't get n plus 1 terms in the expansion like you would think. This I here really does simplify things, and it's amazing. It's an amazing result. you get these multiple angle terms. You get cosine of n theta plus I times sine of n theta for all natural numbers. So this is kind of like the last problem, about the same level of difficulty, not very hard, but you do have to just, keep all of your ducks in a row. So like with the last inequality, check it out, take some values of x greater than -1 and check it out. Just do some indiscriminate checking. You'll find that it's valid. Here, this is again like these number theoretic results when n can get really, really big, just like with the Bernoulli's inequality. You do really want to know that this is valid regardless of the value of n that you choose, because once the n gets so large, you're really relying upon the mathematics, because you may not have the computing ability to understand it, you see? So when we look at this, we're thinking, all right, so what's happening is that when we raise basically a complex or an imaginary number, this is like a real part plus an imaginary part, to the nth power, we get this reduction. That is, we don't get n plus 1 terms, we get cosine of the multiple angle plus I times sine of the multiple angle. So if n, that would be 3 theta plus I times sine 3 theta. Amazing. If it's 2, we get cosine 2 theta plus I sine 2 theta. Oh, angle, cosine of the double angle. Oh, a way to verify trig identities. You're thinking, wow, here's another way to look at trigonometry. So the beauty of this theorem is that it ties together complex analysis and trigonometry in a very intimate way, which if we had time, we could talk about that too. I mean, so that's why some of you need to double major in math so you can spend time studying all these interesting topics to keep happy, so to speak. So when we look at the proof here and we think about this, we could say, okay, well, let n equal 1. This won't be the difficult part. We don't spend much time with this, but we need to start the ball rolling. So we have what? Cosine theta plus I sine theta to the first power. Well, by definition, that's just cosine. And if you like, you can just say 1 theta plus I sine 1 theta. Just put the 1 in there. So you're thinking, well, that wasn't very difficult. That looks good. So 1 is in S, but the idea is that we need the 1 in the proof, or some initial number in the proof for the proof to make sense. So we have to have this. This is, like I say, this starts the ball rolling. If you can at least get an initial check, then there's no need to make an inductive hypothesis, because you haven't even given any reason to give it. You see, you have to have, it's like you check a few things and say, oh, look, this works. Let's move to the induction hypothesis and see if it works for all natural numbers. So this is the reason to start at all. Okay, so this is important. It's not unimportant at all, even though it's not very difficult. It is of I'll just say monumental importance. So for 2, we say for some natural number n, we assume that n is in S. And what does that mean? Well, it just means that cosine theta, I know I'm just repeating myself, but write it down. You write it down in the proof and you'll remember it. Cosine n theta plus I sine n theta. That's the inductive hypothesis. So now we basically have to bump this up 1, and then all the n's get replaced with n plus 1. We don't really need to write that down. That's easy to see. But then you're thinking, oh, addition and subtraction formulas. So this is an excellent application of the addition and subtraction formulas. So we're thinking, if we actually do this, we have to kind of move beyond, so we're not doing circular arguments, but as long as we move to the larger values of the arguments, we might be okay. So just kind of look at this and say, okay, if we apply this, then we can't work backwards in the sense that we're moving circular. It's kind of like doing the logs and the exponents and the laws of logarithms and assuming exponential rules, and our arguments get to be circular, and we're like, we don't like that. So we look forward to calculus to make some sense out of this. So here it looks like we're kind of scratching our back a little bit, but we'll get over it. So now when we look at this, then cosine theta plus I sine theta to the n plus 1, just like we did before, this will now be cosine theta plus I sine theta to the n times cosine theta plus I sine theta to the first power. But of course, just like with Bernoulli, just like with the problems we've already been doing, we can now replace this with the induction hypothesis. That is, this expression equals this by induction. So this equals cosine n theta plus I sine n theta times cosine theta plus I sine theta. So basically, we don't use this to verify pretty much the trig identities. We just see that they're consistent with them because we're going to have to use the addition formulas to move this problem forward. So that wouldn't be like a separate proof. It'd just be a way of saying, oh, you see, we get the same idea, but we don't use that as the starting point. We go back to the arguments that we used in trig where they originated. So now you're saying, okay, we'll just multiply this out and get all these nice terms that we remember from the addition formulas. So let's multiply. So we have what? Cosine n theta times cosine theta. And let's get all the real parts together. Remember, I squared is -1. So if we do the i's here, we're going to get -1. So we're going to get, let me put a minus here because I squared again is -1. So this will be minus sine n theta times sine theta. So when we do this, we get this term. So this is the real part. And then we get the I part. So now let's do that. So in this case, we have, if you like, we got sine theta times cosine n theta, sine theta, cosine n theta. And then the last one, we have plus sine n theta, cosine theta. So we're putting all the real parts and the imaginary parts together. So here, notice here we've got these two which go here. And then the others are just the imaginary parts. So this is a way of saying, okay, if we look at it this way, then we have the real part and the imaginary part, which we need to have here. But now when you look at this, this is the addition formula for cosine. Right here, addition formula for cosine. So this equals, so cosine. So in this case, we have n theta plus theta. This is addition formula for cosine. And here we have the addition formula for sine. Addition formula for sine. So this gives us sine. And then we have the n theta plus the theta. So we can, now of course, when you do Euler's theorem, ladies and gentlemen, you do this based upon analysis. And so this is just kind of a special case. De Moivre looked at this with the roots of unity with the unit circle. And this turns out to be a very elegant application of that. What we're seeing here is that the connection is that all the mathematicians that preceded us saw how the trig and the complex numbers were connected, and how you can't really study complex analysis without defining the trig functions. And the trig functions can be defined in many ways, as you already know right now. And one of them is real analytic ways, which you're going to see more of when you take Calculus 2. So now we're thinking, okay, we're almost there. We're going to factor this. This will be cosine. So we'll do n plus 1 times theta. Just factor the theta out of each of these, plus I times sine n plus 1 theta. So now when we look at this, we see that if we raise cosine plus I sine theta to the n plus 1, we basically get our formula here where the n has been replaced with n plus 1. So this implies that now n plus 1 is ns. We assume true for n, we show true for n plus 1. So by induction, S is all of n. So the key here, again, and you can have some fun with this. You can enjoy working with this. You can basically put in any power here, use the binomial theorem. When we talk about it more, you can use the third power and then pair off the the imaginary and real parts, set them equal, and get some nice trig identities for free. Okay, so the thing is that when we up the value of n, it's a more legitimate way of verifying identities, because we use basically the addition and subtraction formulas, for the basic double angle. So we don't really use it there. We figured those out earlier, but now as we transcend to larger and larger powers of n, it makes sense to equate real and imaginary parts. So this has a lot of nice application, just verifying identities. And I know a lot of you sometimes, there was a multiple angle problem and everybody's trying to do some fancy argument analysis to solve equations, which again, ladies and gentlemen, if it's more difficult to not think the way I've tried to teach you, then don't do it. I mean, the whole idea is that there's nothing wrong with an alternate approach. Even in my last Cal 2 test, I recommended that they multiply two Maclaurin series, but some of them said, to heck with this, Professor Ron, I'm going to use the double angle formula for sine. And of course it was easier. I was trying to see them utilize some college algebra, but I said, okay, that's fine. I said, either way to do it is good. I wanted to see a particular calculation, but I didn't specify that they had to use that method. So it was fine. It's fine. So I'm more than happy to see new methods, but just make sure that you're not exerting too much energy in doing it, that you're not leaving behind something that would execute even more simply. But with that said, you know what? If it gets the job done, fine. At the end of the day, it gets you to the finish line, and I'm fine with that. As long as it's legitimate mathematics, you won't get any complaint from me. Just don't use the slash lines. That does bother me. And I appreciate the notation. For the most part, your notation is good. Your test work that you're submitting, very neatly written, very good. So this is going to be good practice for your engineering classes and your future mathematics classes. So I salute you for that. Now, another example that I think is interesting is the following. So what we're going to do is write down some sequences, and then I may say a little bit about some binomial coefficients that we're going to talk about with the binomial theorem. You're going to love the binomial theorem. It's a really nice result and something that you already know a lot about. So here's a sequence. We're going to say some things about this sequence, and this will be something that you'll see later on when you do your calculus. So we're going to define a recursive sequence. So we're going to set A1 equal to the square root of 2. A2 will be, this would look kind of weird, 2 plus the square root of 2 square root. So we're going to have an inductive type logical statement that we're going to prove by induction, but we're going to define this sequence in a basically recursion is basically an inductive procedure. So we're kind of having the clash of two terms. So A3, again, we see that A2 depends on the previous. That's why we term this recursive. And A3 will look the same. We'll say 2 plus the square root of 2 plus the square root of 2. So after a while, we don't want to have to keep writing this because we run out of room on the paper. So what we're going to do is basically write down what I just said. A sub n will now be the square root of 2 plus the previous element under the radical, etc. So this is the recursive definition. So basically, what do we need when we define something recursively? The Fibonacci sequence is dependent on the previous two elements, which you're going to see in your homework. But here we need the first element and we need the nth element, which only depends on the previous element. So this will get us going. So this sequence is kind of odd, but fairly famous in the sense that it does come up number theoretically and in the calculus. So A sub 1 is the square root of 2, and any element thereafter will just be 2 plus the previous element square rooted. So now if you keep going, you just get square roots embedded in square roots. And that's why I stopped after this, because it just gets a little bit ridiculous to write, but certainly possible. So the idea here is that we have some logical statements. Here's the first one. This one says A n plus 1 is always greater than or equal to A sub n for n element of the natural numbers. And so basically what this is saying is that A sub n is non-decreasing. When I say non-decreasing, it could just sit there, but the elements never get smaller. They either stay the same or they grow. That's called monotonic, okay? Non-decreasing. And you're thinking, yeah, that seems right, but how would I prove it? I've got infinitely many. Well, induction. So when you talk about the monotone convergence theorem in Cal 2, and those of you that take more mathematics, but basically the monotone convergence theorem in calculus 2 says any monotonic sequence which is bounded, for instance, a non-decreasing sequence that is bounded above must converge, okay? That's important because that is the linchpin of all of the convergence theorems for real series in calculus 2. So this is kind of a prelude to that. And hopefully when you get there, it won't be like, what is this? And another one looks like this. These are simple. The second one is A sub n is always bounded above by 2. So we'll just say bounded sequence. So basically from this, if this is non-decreasing, that would be a lower bound and this is an upper bound, so to speak. So your thinking is to the limit of this sequence. Well, that's something you'll be able to prove when you get to calculus. Right now, we don't have the calculus, and I could talk about it, but that's, that'll be something that you'll get to eventually. This will give you plenty of preliminary information about it. And if you want to investigate some of this more, you certainly have that opportunity before you get to calculus 2. So the idea, let's call this 1 and call this 2. So for 1, proof. Now, lots of times students will, you'll have algebraic formulas where they may be all tied up with natural numbers, and you might think, well, I don't need induction. I can do this algebraically. No problem with that. Sometimes the algebraic approach is the best approach. Sometimes you'll use calculus to show non-decreasing. I mean, it really just depends on how complicated expressions are. And so you'll take the calculus and supply the arguments you need. You'll do some basic algebra. But when you're dealing with sequences and you've got a situation that doesn't necessarily lend itself to calculus, okay? Maybe it's not quite, that algebraic flair that makes the application of the calculus work. This is a recursive situation. It's kind of like the towers of Hanoi. You can't really look at it in a very simple way that makes the analysis the way you would like it. So what we want to do here is say, okay, let's prove that this is non-decreasing just by going through the inductive step. Number 1, we'll let n equal 1. Okay, so a sub, well, let's just be simple. Let's just be easy. Let's not even worry about that. Let's just make this so simple. Let's do this. We'll just know the following. We'll say square root of 2 is what? How do I want to do this? Yeah, let me look at it this way. Let's just say, let's look at this and say this. Let's just go under the radical. This will work. Let's do this. 2 plus square root 2 is greater than 2. I think that's true. So when you look at this, you're thinking, okay, well, Professor Ron, you get the Nobel Prize. Well, when you look at this, you say, okay, 2 plus the square root of 2 is certainly bigger than 2 because the square root of 2 is bigger than 0. So that's true. And now this implies, let's apply the square root, which is an increasing function. So it will basically preserve this inequality. So we have the square root of 2 plus square root 2 will be greater than or equal to the square root of 2. So if this is greater than this, the square root function will preserve this, because again, if this is bigger than this, then the increasing function will say that the output of well, this is the definition of a sub 2, and this is the definition of a sub 1. Okay, so yeah, so for n equal 1, a sub 2 is bigger than a sub 1. So this implies that 1 is in S. I mean, that's the best we can do. So clearly the first term is bigger than the second term. Even though that seems a little bit untoward, it's how you do it. I mean, it's certainly an inductive procedure. So now 2, for some natural number, n, we assume that n is in S. We're assuming that S contains all the natural numbers for which this is true. So what does that mean? That means that a sub n plus 1 is greater than or equal to a sub n. That's the inductive hypothesis. So now when you think about this and you look at this, you're thinking, okay, we need to bump this up 1. So now we need to bump this up by 1. So let's just see what that'll do. And this is going to be easy to do. So now we're going to start with this and add 2 to it. Then I change this up every time I do it. So we'll just say in this case, making it look like that, 2 plus a sub n plus 1 is certainly greater than or equal to 2 plus a sub n. And this is by induction hypothesis. Because of course, if a sub n plus 1 is greater than or equal to a sub n, then I can certainly add 2 to both sides and preserve that. So that's the induction hypothesis. Now we want to apply the square root. So I'll write this, apply square root. It will preserve the inequality. So we have what? Square root of 2 plus a n plus 1 is greater than or equal to square root 2 plus a sub n. So all the indices are bumped up by 1, that's okay. But what does that mean? By definition, we just go up to here. This is a sub n plus 2 is greater than a sub n plus 1. So if I assume that the n plus first term is bigger than the nth term, that helps me to show that the n plus second term is bigger than the n plus first term. So this implies n plus 1 is ns. Oh, let me get the 1 first before we write the s, Professor Ron. There we go. So even though this is simple, it's different. You're thinking, this is not hard at all. It's just basic common sense. But common sense is hard because it's a different way of thinking. Because we don't have a whole lot of work here, but we're thinking, how can we get the fact that now we know this is non-decreasing, but had we tried to do it any other way, we would have found impossibility. So we say by induction, S is all of n. So this is a non-decreasing sequence. When you look at it, you think, yeah, that makes sense. It looks like the terms never get smaller. They're either, they're gradually growing. Okay, they're gradually growing. So again, induction here is very powerful. And you can, this is clearly not unique. I just set this up to be very straightforward. And I've got the subscript set up to be easy to follow. So this is just following the recipe, so to speak. Now, let's look at the next part. So what's left? We need to show, okay, so we got all of this. So now we need to show that it's bounded. Okay, so let's do 2. And I'll do this right below it where I've got it written so you can see it. I don't have to write it again. So now we have, we want to prove 2. So 1, n equals 1. Okay, well, let's just look at this. Here we go. If you like, square root 2 is less than or equal to 2. We know that's true. The square root of 2 is the number that we multiply by itself to get to, and these two numbers are related to each other by this. Square root 2 is actually strictly less than 2 by definition, but here we go. But again, why do we know that? Well, 2 is bigger than 1. Okay, it's a weird thing because of course when you get between 0 and 1, things flip around. Okay, so when you look at this, we observe this just by the nature of the real numbers. That is, square root of 2 by definition is less than or equal to 2. So equivalently, this just says A1 is less than or equal to 2. And that's kind of like, this is like given, so to speak. This is given. So this implies 1 is in S. And you don't, oh, well, I substituted, I punched it in my calculator and it's true. No, we don't do that. If you have to do that, then your reasoning's not correct. This is true by definition. So again, and basically what we know about real numbers. So we start off by saying, well, I agree there, but what about all this stuff? What's going on here? Do we have that? Well, let's try it by induction. So 2, and if it falls apart, then so be it. So now for some natural number, we suppose, and I guess I always write it this way. Do I always do my, for some natural number? Yeah, I just say comma. N is in S. I usually write it that way. Or you could write suppose. What does this mean? This means this. A sub n is less than or equal to 2. Now, what we want to do is take an interesting step here and just look at this and say, okay, if this is true, can I use the definition of the next or the successor to utilize this? So at this point, think n plus 1. Just like, but again, it's a little bit more subtle. So we can say, okay, then by definition, a sub n plus 1, well, let's just go up to the definition. It equals this. The square root of 2 plus a sub n. Now, when we look at this, we're thinking, okay, well, we have an upper bound of 2 for a sub n by induction. So this will be less than or equal to. So I'm going to make this number bigger by hypothesis. So this is induction hypothesis. So this will be 2 plus 2. That is, a sub n is less than or equal to 2. So I can get an upper bound here by replacing a sub n with 2. But that just equals square root of 4, which is 2. So this implies, again, a sub n plus 1 is also less than 2. So n plus 1 is in S. So this is a very elegant application of induction. Now, I will say this. This is a little bit different, kind of like when we were doing the divisibility argument. We had to add and subtract a convenient term. You have to look at this by saying, okay, what do I have to assume and what do I need to do with it? Sometimes the amount of work you need to do is minimal. It's like, well, I didn't really do anything, Professor Ron. Look how little we had to do to prove this. Sometimes the answer is right there. It basically hinges on the induction principle. It's so straightforward that you're thinking, what did I do? You use the power of the induction principle, okay? Let me say that again. You use the power of the induction principle. Sometimes it's like, it's just a matter of turning the page of a book. It's like, that's all it is, kids. But you have to invoke it to move forward. You can't just say, well, you know, don't you see this as obvious? That's not a proof. Well, clearly, that's not a proof. I mean, if I ever say clearly, it's because I proved it a million times and I'm not going to prove it again, okay? So now we can see by induction, how funny, by induction, S is all of N. So this is where you get to number theoretic constructs and you're starting to think, man, this is really some crazy stuff. But these are types of arguments that ensue when you think about recursive algorithms in computer science. They're used all the time. When you think about those, you know, you think about, oh, well, I want to use some computer science. I want to use some math. I'm not really sure where it's going to go. Am I going to get into biomedical engineering or do I want to do computer engineering, or am I just so crazy about math that I'm just going to do strict computer science? Who knows? You know, you're still trying to make up your minds, and that's fine. But just now, what I want you to see is that if we learn induction, then we can apply induction to maybe the binomial theorem when we just work it for natural numbers. So you're thinking this can be a way to validate the binomial theorem. But when I say induction is a way to prove logical statements about natural numbers, I'm not saying it's the only way. you can sometimes use a combinatorial argument, which will affect the same kind of reasoning and push forward a proof. Those of you in computer science will do some combinatorial mathematics, and we'll be doing some of that at our next lecture. So the neat part about calculus is that it does use discrete concepts like binomial coefficients. It uses sequential arguments, okay, like we just did here. So you can't separate the two. You can't say that an engineering student's never going to need any number theory. I mean, that's not true. You can't say that a computer science is never going to need to do an integral. That's not true. You're thinking, well, they're going to spend most of their time with number theory. They're going to spend most of their time with integrals. Maybe that's true, but they often come together and you have to know some about everything. So that's why the STEM major gets, just barraged from all disciplines of mathematics: algebra, geometry, number theory, analysis, complex analysis, combinatorics, topology, differential geometry. You get some of that in the calculus sequence. You can't avoid it. It's just all there. And then if you take more math, then you will get into more detail in those areas. But engineering, science, computer science, it draws in all disciplines of mathematics. And so I hope today that you at least have developed the appreciation for the induction principle. Basically, is it true for one? Is one in S? And if we assume N is in S or K, you can use K, I don't care. K is in S, does that mean N plus one or K plus one is in S? If you can verify those two steps, then you have validity for all natural numbers. And what's the key? The second step, the induction step, is the most difficult. We see in this case, piece of cake, not very hard at all. When we look at previous examples, we see the induction step might require a little bit more work. But the idea is that none of these induction steps are unique. Okay, if you fashion an argument, then that's good. Now, of course, when you're working on your homework, you may have to kind of follow the ideas of an argument, of an induction step, which they'll be valid. And so you'll have to follow that reasoning. But you can go to the side and once you've completed the problem and work out a completely analogous, legitimate calculation that will do the same. Okay, so just remember as you work through your homework, you're just kind of following the algorithm of the problem. And then it may say, well, prove this by induction. And so you may do your own proof and then say, check, this works or this doesn't work, kind of thing. So just remember, if you're following an argument that's already set up, then program yourself to say, okay, they've assumed this, so I need to use this to move to this step, and it'll be very algorithmic. So just remember, mathematics doesn't mean that you do everything the same as someone else. It just means that you use legitimate techniques that are valid. When I say legitimate techniques, techniques that are understandable, techniques that are mathematically sound, that move you through the process. So I hope you have enjoyed this today. It's kind of fun to do induction. And I know that it's a little bit different, but it is something that you will see again, and it's something that you need to be exposed to. So I hope you've enjoyed the step into the infinite and to the abstract, but Professor Ron kept it as unabstract as he could. So I hope this will be something that you will enjoy in this class and in future classes. So I'll send out some invitations today for conference hours. I'm glad that you were able to make it to class today, and don't forget about your signature assignment, okay? We'll see you soon. Take care.